Alright guys, we are finishing up chapter 1 today with sections 1.9 talking about unit vectors and section 1.10 talking about the products of vectors. Pretty exciting and useful stuff. So let's get started and finish chapter 1. Okay, unit vector. Unit vector is going to be a special vector. It's still a vector and it's pretty ordinary, but it's special because it has a magnitude of 1 and its only purpose is to point in a specific direction. Again, that's all a unit vector is. A special vector with the magnitude of 1 that just points in a specific direction. Now, I'm just going to quickly write out some unit vectors that you're most likely going to see. So you're going to see x hat, and this is how we denote unit vectors. We have the little caret on top, x hat, y hat, and, whoops, got ahead of myself, and z hat. Those are like our standard unit vectors for a Cartesian coordinate, which is just this. And you're also going to see these written as I hat, j hat, and k hat. These are the first couple set of unit vectors that we're going to be working with. And just to make it even clear, x hat and I hat are going to be the same thing, y hat and j hat are going to be the same thing, z hat and k hat are going to be the same thing. So now that I've shown you how they're written, let me show you what they look like on a graph. So remember, it's a magnitude of 1, and it just points in a specific direction. X hat points in the x direction. Y hat points in the y direction. And z hat points in the z direction. These vectors are just used to specify direction. Now, like I was saying, you might see these written as I hat in the x direction, j hat in the y direction, and k hat in the z direction. Either way, they're going to be talking about the same things. Now, the reason unit vectors are so useful is because I now have a really neat way to describe the vector r. So remember how each vector has an x component, a y component, and a z component? Well, now I can neatly decompose this vector into its specific components. Now, I'm actually going to go ahead and use the I hat, j hat, k hat notation because it's the one that's most commonly used in advanced textbooks. I don't know why, that's just the one they use. Got it. So this is a general vector. You can write any vector in this format, and that is the power of unit vectors. Like, I cannot stress it enough, just how useful unit vectors make life. They are awesome. Okay, so let's go on to one more thing we're going to quickly cover here, and that is, let's say we have this vector r hat, which is composed of two separate vectors added together. I can write this, as we covered earlier in an earlier section, I can write this as ax plus bx in the I hat direction plus, whoops, ay by in the j hat direction plus az bz in the k hat direction. And notice how these are just the x, the y, and the z components of our r vector. That is how you would do vector addition using these unit vectors. So now that we understand this, let's just quickly cover example 1.6. Okay, so here we are at example 1.6, and it goes as follows. Given the two displacements, d hat and e hat here, find the magnitude of the displacement 2d minus e. Cool, pretty straightforward. Let's just dive in. I'm going to call the displacement s hat, which is going to be equal to d minus s vector. So let's just quickly solve this. So it's going to be 2 times d. Now guys, I would definitely recommend, whenever I'm writing, to just put me on 2 times speed. That's what I would always do. Probably just put me on 2 times speed in general. Okay, it's going to go something like this. Now we do the subtraction or addition. That's going to be our displacement vector. Now we have to find its magnitude. And that is just our equation, our Pythagorean equation in 3 dimensions now, but it's still the same thing. And I am leaving out the units all the way up until the very end. And if you plug this into your calculator, you are going to get the following. And that is very quickly our solution to example 1.6. Now, let's move on to the test your understanding section. Okay, so here we are. Arrange the following vectors in order of their magnitude, with the largest vector going first. And these are our 4 options. Now, I want you to just take a second to look at these options, because you should be able to solve this problem in under 10 seconds, just by looking at these vectors. Okay, so let me tell you why. These vectors have the exact same components. It's just in different vectors, they're positive, and in the others, they're negative. But the answer is that they, and let me write that in the appropriate color, they all have the same magnitude. You don't even need to do math. All you need to do is look at their components, and you see that they're the same but with different signs. But when you go and plug them into the equation for magnitude, it doesn't matter if they're different signs because they get squared. Therefore, they all have the same magnitude. Cool. That's it for section 1.9. Let's move on to section 1.10. Okay, so here we are, and we're going to start off by discussing the scalar product, sometimes called the dot product, although in my experience it's called the dot product more than it is the scalar product. And let's go ahead and let's start by defining that. So the scalar product is written like this, A dot B. Now remember, we're talking about vectors here. If I were to like multiply regular numbers, it's just like this, and they can all be multiplied in a pretty regular fashion that you're used to. But with vectors, it's a bit different. We multiply them using the scalar product or the vector product, which we'll talk about later. But let's continue. A dot B, the scalar product, is equal to the magnitude of A times the magnitude of B times the cosine of theta of A and B. Now, let's unpack this. Let's draw a diagram, okay? Let's say we have vector B here, and let's say we have vector A here. And let's say that this is the angle between the two vectors. One thing to note, this angle here is referring to this angle, the smallest angle in between them. It is not ever referring to this angle, the largest angle in between the two vectors. Now, one way we can sort of look at this is to draw this dashed line here going down, and you should notice that this section right here is the magnitude of B cosine theta AB. It is the x component of B in a sense, or it is the, let's write this down, this is the component of B projected onto A. That is what this drawing illustrates here. Now, we can use that to gain a little bit of knowledge about this scalar product. We can define it as the magnitude of A, which is what that is, the magnitude of A times the component of B projected onto A. And it also works in reverse. You could look at it as the magnitude of B times the component of A projected onto B. Now let's go into 3 case scenarios with this scalar product here. There's going to be a time in which the scalar product is less than 0. There's going to be a time in which the scalar product is greater than 0. And there's going to be a time in which the scalar product is equal to 0. Now, an important thing to note here is that, back to the definition up here, the scalar product actually returns a number. And I want you to appreciate that really quickly. Like, you multiplied a vector by another vector in a specific way, and you got a scalar. Like, you went from having information in 3 separate dimensions, and now you just have a number. So interesting. In a way, you lost information. You went from having vectors to just a number. That's curious. And maybe we'll learn about that in more advanced physics. But let's continue. A dot B is greater than 0. When is A dot B greater than 0? Well, let's look at our definition. The magnitudes multiplied by each other are always going to be positive. So we can just not even consider those. The thing that determines whether or not A dot B is greater than 0, less than 0, or equal to 0 is the cosine, because it's the only thing that is going to change in sign. So we have to ask ourselves, when is cosine greater than 0? When is it less than 0? And when is it equal to 0? And that would be in the following. Let's draw 3 diagrams here. These are unit circles, and they're going to represent our 3 scenarios. Now, cosine of theta, AB, is greater than 0 when cosine lies within this half of the sphere, because this is where it is positive. Now, when is that? That's going to be when theta is less than pi halves. This is pi halves, and it is when theta is greater than negative pi halves. This is negative pi halves, pi halves. Cool. I hope that makes sense. Let me get rid of that. Okay. When is cosine less than 0? Well, it's going to be the inverse, pretty much what we just did. It is going to be when it's on the left half over here. And this again is pi halves, and this is negative pi halves. And that's all we pretty much need to do. So it is theta greater than pi halves. But it would be a mistake now to say, but less than negative pi halves, because that would bring us to this sphere here. What we have to do is say that it is less than 3 pi halves. Negative pi halves and 3 pi halves lead you to the same destination. Just one is counterclockwise and the other is clockwise. Cool. So now we ask ourselves, when is theta, cosine of theta, equal to 0? Well, that is when it lies on these points here. And that is also when sine of theta is at its maximum. So those are the 90 degrees and then the 270 degrees. So this is when theta is equal to pi halves or n pi halves. Let me get rid of that. Where n, now here's the tricky part. You have to define n such that it can get you whole numbers of pi. So for example, we know that cosine of pi is -1. So n can't be any multiple of 2, because that'll get us whole numbers of pi. So n has to be odd. Does that make sense? Because let's say n equals 1. Well, that's just pi halves. Cosine of pi halves is equal to 0. N equal to 3. That's 3 pi halves. Cosine of 3 pi halves is also equal to 0. And it just keeps on going like that. Now, let's take a look at this last section once again, because it tells us something else. It tells us that when 2 vectors that are at 90 degrees angle, or any multiple of 90 degrees, that is to say that when they're perpendicular to each other, this is the sign for perpendicular, they will always have a scalar product of 0, which is very, very important. It sounds so simple, but it does have important consequences, which we're about to cover now. Okay, so we're going to use components to calculate the scalar product, and it's going to look something like this. A dot B. Now let's write out our x vector. Again, have to remember to use the more classically used unit vectors. That's A. Now, I just realized I wrote that completely wrong. Let me fix that. There you go. Okay, this is what A dot B looks like when we write out our vectors. Cool. So let's just do multiplication. And the way we do this is we take the x component and we just multiply it by the first x component, the y component of B, and then the z component. And we do the same for all the other components. We multiply each one to each side, just like standard factoring and regular mathematics. So let's write it out. And again, I would recommend you to put me on 2 times speed here. Okay, so if you multiply it all out, that's what this becomes. Now, the thing about the way it's written here is that it doesn't really illustrate anything. So I'm going to take a second. I'm going to rewrite this completely to show you something more innovative, something more with meaning. So let me go ahead and do that. Okay, so here we go, and I've rewritten it in a more revealing way. So what I've basically done is I took this component and I made the realization that, hey, ax and bx are just scalars. They just multiply to each other in a normal fashion. The dot product only exists between vectors. So I grouped up the 2 unit vectors here and their dot product. Now, the reason that this is more insightful, and I want to go ahead and I did it for every single term. This is more insightful, not only because it clearly shows that scalars are being multiplied by scalars and unit vectors by unit vectors, but also because it just simplifies what we need to do. And what we need to do is, well, we pretty much know that scalar multiplication is going to be what it is. But what we need to solve for are all these unit vector scalar products. And we're going to use that third rule that we just talked about. Remember when I said that it would be important to know that 2 vectors that are at 90-degree angles with each other always have a scalar product of 0. And I'm about to show you why. That makes our work super, super simple. So let me draw out a couple of things for you. Okay, so here we are, and I've drawn out our regular Cartesian coordinate. Now, remember, these unit vectors are all on a specified direction, specifically the y, the z, and the x direction. And remember, on these coordinate systems, these angles, these unit vectors are all 90 degrees to one another. So do you know what that means? That means that whenever we do the dot product between any of these vectors, such as I dot j, or I dot k, or j dot k, since they're all at 90 degrees to each other, their dot product is equal to 0. And what that's going to do is that pretty much anytime we see a unit vector dot product with a unit vector that's not itself, such as these cases, and here, all of these are going to equal to 0, and the whole term just goes away. Now, what we're left with are these terms where the unit vectors are scalar product with themselves. Now, what does that equal? Well, remember how a unit vector is just one direction. So if its dot product is with itself, that means that the angle between it is just 180 degrees. They're parallel. There's technically no angle in between it, but in that case scenario, we just call it parallel. Now, when two angles are parallel, and let's say we have their definition here, the theta, the angle between them, is 0, right? Or, as I just said, or it's 180 degrees. Because let's say they were like this, that's 180 degrees, or if they're exactly the same, this angle is 0. I hope that makes sense. In that case scenario, cosine of 0 or cosine of 180 is equal to 1 or negative 1. But in this case, it's equal to 1 because our unit vectors are all positive and neither of them are in the opposite direction. So what this tells us is that I hat dot I hat is equal to j hat dot j hat is equal to k hat dot k hat, which is equal to 1. Okay. So this becomes 1, this becomes 1, this becomes 1. And I hope you can see that all we're left with are these scalars multiplied by one another. So let me simplify down our equation. Now, after all that, after all 9 of those terms, all we're left with is 3 terms in which we multiply scalars by one another. So this is going to be a pretty useful formula. And now we have 2 formulas with which we use to calculate the dot product. So let's go ahead and put these to the test, and let's work on an example problem. Okay, so here we are. Example 1.9. Find the scalar product A dot B of the 2 vectors, and their magnitudes are given as follows. The magnitude of A is 4, the magnitude of B is 5. And here are the vectors. Okay, so here we are. We have vector A here, vector B here. Vector A makes an angle of 53 degrees with the x-axis, and vector B makes a counterclockwise angle of 130 degrees with the x-axis. Now, we have to find the angle between A and B, which is going to be 130.0 degrees minus 53.0 degrees, and that is going to equal 77 degrees. Did I do that right? I think that's correct. Yeah, 77 degrees. Actually, that's incorrect. 77.0 degrees. There we go. So now it's really easy. Now we just pretty much plug our numbers into this formula. Since they gave us the magnitude, this is the easier formula to use rather than finding the components and then multiplying terms. So this is going to be 4.0 times 5.0 times cosine of 77.0. Let's just calculate that real quick. It's going to be 4.50. Cool. And that is your answer for example 1.9. Okay, let's move on to example 1.10. It's pretty simple. It just lays it out, find the angle between the 2 vectors. Now, it laid out our vectors in component form, which means we're most likely going to need to do component multiplication. Okay, so let's remember our 2 formulas. A dot B is equal to AX BX plus AY BY plus AZ BZ, and A dot B is equal to the magnitude of A times the magnitude of B cosine of the angle between them. Cool. We can pretty much set these equal to one another, and that's the same as saying A dot B is obviously equal to A dot B, which is the same as AX BX plus AY BY plus AZ BZ is equal to the magnitude of A times the magnitude of B cosine of the angle between them. And now what we need to do is get the angle by itself. So let's do that. You divide by A times B, the magnitudes on both sides, and you should get the following. AX, BX plus AY, BY plus AZ, BZ divided by the magnitudes. And now we have to do the inverse cosine on each side to get the angle by itself. And I want you to pay attention to what I'm doing here. I'm solving out the problem symbolically all the way to the end before I plug in any numbers. And the reason we're doing this is because we have to get used to it. Because in advanced studies, you deal with symbols more than you deal with numbers. And now all we need to do is plug in all of our numbers, plug in all of our equations, and it's going to look something like this. Remember that the magnitude formula involves a big square root. Okay, if you plug all of these numbers into your calculator, you should get that the angle between the two vectors is 100 degrees. And that is your answer for this example problem 1.10. Now we're going to move on to the second way in which we multiply vectors, and that is through this vector product, which we define as A cross B. Oh yeah, this is also sometimes called the cross product. A cross B. Cool. Now, A cross B is going to be defined as a very big thing. Let's go ahead and explicitly write it out for you. Now, we can solve this equation similar to the way that we solved the scalar product. And we will do that, but before we do that, we're going to gain some intuition as to what this ends up being. So, we defined the magnitude of the scalar product to be very similar to the magnitude of the vector product to be similar to what it is for the cross product. Okay, so the magnitude of the cross product is equal to AB sine theta AB, which is the magnitudes of a, let me rewrite that. So remember, this is the magnitude of the cross product is equal to this. And just as we did for the scalar product, let's go ahead and visualize it. Okay, so this is your angle. Okay, so now since we're dealing with sine, we have to take this component. And what this tells us is that this term here is simply the component of B that is perpendicular to A. So you can reason that the magnitude of the cross product between A and B is equal to the magnitude of A times the component of B that is perpendicular to A. And that gives you a little bit of insight. Now, let's go ahead and erase all this, and let's solve our equation in the similar fashion that we did for the scalar product. So let's get started with the big multiplication. Now I'm going to go ahead and take a shortcut and just write it in the simplified, beautiful manner in which I did for the scalar product. Okay, so this is what this multiplies out to be. And remember, this is just standard old multiplication of two numbers. What we're focusing on are these terms right here, where the unit vectors are crossed to unit vectors. And what we need to do is find out what those are. So let's write them down. Okay, so in order to solve this, we need to do the similar thing to what we did with the scalar product. And that is, ask ourselves, when is the magnitude of A cross B less than 0? When is it greater than 0? And when is it equal to 0? Again, the answer to this is going to rely all on the component which has the angle, which is sine theta. So let's go ahead and visualize these with unit circles once again. Okay, so when is sine of theta less than 0? That's going to be in this component right here, which is bounded by 0 and pi. So the cross product is less than 0 when sine of theta is less than 0, and that is when when theta is greater than pi, but less than 2 pi, or 0, same thing. Now, it is greater than 0 in this area right here, again, bounded by 0 pi. So a cross b is greater than 0 when sine of theta is greater than 0, and that is when theta is greater than 0, but less than pi. Now, the third section, when is a cross b equal to 0? That would be in these sections right here when the sine of theta is also equal to 0. And that's pretty much when theta is either equal to 0 or any multiple of pi. Cool. Now, again, this tells us something much, much deeper than what is present at the surface. And that is that when two vectors, are parallel, their cross product is always 0. And that's visible here because parallel vectors have an angle of 0 between them or an angle of 180, which is the same as pi. So how can we use this? Well, vectors that are parallel are pretty much vectors in the same direction or in the opposite direction. That means that I cross I is equal to j cross j, which is equal to k cross I. This is the cross product between vectors that are parallel, which is 0. So from that, we know that these components of following this diagonal are 0. They just get removed. Cool. That leaves us with 6 more terms. And in order to solve those, we have to introduce the right-hand rule for cross products. Now, the right-hand rule, I hope you will understand when I'm writing it down. This is a rule that's very easy to show. It's better to show in person. So let's say we have this k cross I hat, and here's k, and here's I hat. Now, the important thing that I want you to know about cross products are that when you cross product two vectors, what you get is actually another vector. And this vector, let's call it C, is perpendicular to your factors, which are k and I. Now, in order for that to be true, there are two directions in which C can come out of. Because remember, you have these two vectors, k, unit vectors, k and I hat, which lie on the same plane. They're both on the flat zx plane. It's a flat area. So for a vector named C, in order for it to be perpendicular to both of this vector, it's the same thing as saying that this vector has to be perpendicular to the entire plane. And that can only happen if it's in two directions. It's either going up or it's going down out of the plane. And the right-hand rule pretty much lets us know if it's either going up or down, into or out of the plane. So let me go ahead and tell you what that is. So the right-hand rule is going to state that you're going to pretend as if you're coiling your fingers. If you have it written as k cross I, you start at k, you curl your fingers from your right hand to the second vector, which is I hat. Now when you do that, the direction in which your thumb is pointed, which should be up, is the same direction as your resultant vector. So in this case, vector C points in the j hat direction. Now, if you were to do I cross k, it would point, vector C points in the negative j hat direction. And what we learn from that is that cross products are anti-commutative. That is to say that A hat cross B hat is equal to the negative of B hat cross A hat. Cross products are anti-commutative. Now, how can we use this to help us solve the 6 leftover terms? Well, we just saw here that when we crossed K and I, we got a resulting vector in the j hat direction, which makes use of our all 3 letters, K, J, I. So let me explain to you now a couple of things. Let's do I hat cross j hat, which uz is a term that is used here. So let's solve for that. That is going to give us a vector, and we know that it is in the direction of k hat. Now, what you should be asking yourself is, well, if we know that it's in the direction of k hat, that's cool. But what is the magnitude? Now, I'm going to take you on to the initial formula that we used. Let's say it's the magnitude of j times the magnitude of I, sine of the angle between I hat and j hat. We know that their magnitudes are 1 because they're unit vectors. Now, that just leaves us with the angle between them, which, since they're unit vectors, they're perpendicular to each other, we know that that angle is 90 degrees, which is equal to 1. So right here, we've just found that the magnitude of this cross product is equal to 1. So now we know its magnitude and its direction. So that gives us I hat cross j hat is equal to k hat, because 1 is just 1. Cool. And since we know that cross products are anti-commutative, we know that j cross I is equal to negative k hat. Now, we're going to do the same thing for the remaining 4 terms. For example, I hat cross k hat is equal to negative j hat, and k hat cross I hat is equal to j hat. And j hat cross k hat is equal to I hat, and k hat cross j hat is equal to negative I hat. Awesome. So let's go ahead and substitute these values in to our equation. Now, I'm just going to go ahead and rewrite them, and erase them and then rewrite them. So I hat cross j is just going to be k hat. I hat cross k is just going to be negative j hat. J hat cross I is simply going to be negative k hat. J cross k is I hat. K cross I, that's going to be j hat. And k cross j is going to be negative I hat. So you know you did this right if you have a positive unit vector and then a negative unit vector. So each unit vector should have both a positive and a negative version. Cool. So let's go ahead and write this in a more simplified manner. Okay. And if you go ahead and group the like unit vectors together, this is what you get. Now, I will say one thing. This second term, you're actually going to see it as written in a different way in some textbooks and in some cases. And I actually prefer that it is written in this different way. So I'm going to show you right now. I'm going to rewrite this entire thing and I'll show you what my preferred method of writing it is. Okay, so here we are. And as you can see, all we did is we made this into a negative. And so we had to take the negative out of this term and we just switched the components around. Now, the reason that this works better and that I prefer is it comes down to the way, there's a different way to calculate the cross product than what we just did. And when we use that different way, it becomes easier to visualize why this second form is the way that it is. But we're not going to talk about that today and in this video, perhaps in another time. For now, let's just move on. Now, since we know that A cross B gives us another vector, I'm just going to go ahead and write out that vector, we're going to call it C. And from this equation, we can see that this is just Cx, this is just Cy, and this is just Cz. I hope that makes sense. Now, knowing all of this, we're going to go ahead and tackle an example problem. Okay, so here we are at example 1.11. Vector A has a magnitude of 6 units and is in the positive x direction. Vector B has a magnitude of 4 units and is in the xy plane, making a 30-degree angle with the positive x-axis. Find a vector C that is equal to A cross B. Cool. Now let's go ahead and try to do this without a diagram. Since we know that A has a magnitude of 6, B has a magnitude of 4, and that A is only in the positive x direction, and that B makes a 30-degree angle with the x-axis, that's the same as saying that the angle between A and B is equal to 30 degrees. Now, we pretty much have what we need to calculate the cross product. We have magnitudes and we have the angle. So we're going to use this simple equation, which I hope you remember. Actually, if it's your first time being introduced to them, it's okay if you don't remember. Sine of 30 degrees, and that's going to give us A cross B is equal to C, which is equal to 12. Now, the thing about this equation that I always forget to write in is that this is just a magnitude. So we got that the magnitude of C is 12. Now the question to ask is, in what direction? Now again, we're going to try to do this without the diagram. So we know that B is in the xy plane. So let's just say this is your xy plane. Let's say this is x, this is y, and you know that A is in the x-axis. So you have a vector on the x-axis and a vector somewhere here in the xy plane. That can only mean one thing, that your resultant vector, the C vector, has to be pointing either up or down out of the plane. So in which direction? Well, remember, it's A cross B, and we know that A is on the x-axis. This is your y. So we know that A is here on this axis, and we know that B is somewhere along here. If we do the right-hand rule, A cross B, we're going to be curling A this way, and our thumb is going to be pointing up. And up is the k-hat direction. So we know now the magnitude and the direction. So we know that C vector is equal to 12 k-hat. And that's going to be your answer for example 1.11. Let's move on to testing our understanding of section 1.10. Okay, so here we are. And it goes like this. Vector A has a magnitude of 2, important to remember, and vector B is a magnitude of 3. The angle theta AB, phi AB, can be either 0, 90 degrees, or 180 degrees. Find theta of AB for each of the following. A dot B is equal to 0, A cross B is equal to 0, A dot B is equal to 6, A dot B is equal to negative 6, and the magnitude of A cross B is equal to 6. Cool. All right. So we know the magnitudes of A is 2 and the magnitude of B is 3. And that pretty much tells us that what we need to focus on is the cosine. So let's start with part A. A dot B is equal to 0. Remember, this is the dot product. The dot product has to do with cosine of theta. Remember that. Dot product is cosine. Sine is the cross product. So for number 1, it's a dot product. We're talking about cosine. Now, the dot product between A and B is equal to 0. That only happens when the cosine itself is equal to 0. And out of these 3 choices, that's simply going to be 90 degrees. Cool. Moving on to part B. A cross B is equal to 0. So that's the same thing as saying that the sine of phi of A and B is equal to 0. That's going to happen at the following 2 angles, either 0 or 180. Part C, a dot b is equal to 6. That only happens if the cosine of the angle is equal to 1. And that's going to happen when the angle is 0. Part D, a dot b is equal to negative 6. This is sort of like the opposite scenario. That means that the cosine of the angle is equal to negative 1. This happens at 180 degrees. Now, the magnitude of the cross product between A and B is equal to 6. That happens when the sine of the angle between them is equal to 1, which happens at 90 degrees. Now, that's going to be your answers for the testing your understanding of section 1.10. And with that, we wrap up the entirety of chapter 1. So congratulations. I will see you later as we tackle on every single problem in chapter 1. Yes, I mean that we're going to do every problem. So I hope you're ready.